Okay, so let's take a look at comparing our different major functions that we've covered in this course. We have linear functions, quadratics, and exponentials. First of all, we know what a linear function looks like. It's going to be your function that comes across in a straight line on your set of axes. So it's either going to look like this if it's positive, or it's going to look like this if it's negative, or it might even just be a nice horizontal line straight across if it's constant. It'll either way, the way that we can tell that it's a linear function or that it's a straight line it's always increasing or decreasing, but not both, or constant. And the equation of our straight line right from grade 9 was y equals mx plus b. Now we might have b or m equal to 0 at this point, so I might end up with a line with a linear function, say, that looks like, for example, y equals 6x, or y equals 7, or y equals 6x plus 7, or any kind of combination. I could have y equals negative 3x plus 7, y equals negative 3x plus 100. Either way, what I'm seeing here is I'm seeing an x in my equation, and there's no exponent on that. Now, a quadratic equation, we've been working with those as well for a long time here. The way we can tell a quadratic equation is it will be increasing then decreasing if we look from left to right. So if it's increasing then decreasing, it'll look like an opening down parabola, or it might be decreasing and then increasing, in which case we have a minimum value there, and it's either way, what it's going to do, it's going to change direction at a vertex at some point. So it changes direction. And it's not a straight line here, it's a curve. We need to be careful when we're drawing in our parabola. It's always going to be a smooth curve. The equations, well, we've taken a look at the equations of quadratics a number of times in here, so we can have it in, say, standard form, which is y equals ax squared plus bx plus c, or in vertex form, so y equals a x minus h squared plus k, or I can have it in factored form, y equals a x minus s x minus t, where s and t are my zeros. So examples of something of a quadratic equation might be y equals negative x plus 1 squared plus 7. Either way, what we're going to see in a quadratic equation is we're going to see an exponent equals 2, and in the base of our exponent will be an x. Additionally, just one more thing that we do notice about our quadratic equation that's not going to be true for linear or for exponential is that it has some symmetry. So about the vertex, it's symmetric. And lastly, let's take a quick look at our exponential equations. So these will be similar to our linear equation, that it will always be increasing or decreasing. But not both. And similar to the quadratic, it'll be a smooth curve. And relative to the quadratic, it will get steeper faster than the quadratic will. So an example of an exponential function, I might have something that looks like this, and I can see that it's very steep right around this part of my equation, of my curve. Or I might have something that looks like this as an exponential as well. The equation of an exponential will be y equals a b to the exponent x plus a c, where to be honest, the ones we've been working with, we've always had c equals 0, so we haven't even had that part of our equation. Our equations will look like this. We can identify them because our x is in the exponent this time. Our x is not the base. Our x is always written nice and small up there in the exponent. X in exponent. As long as your x is in the exponent, then you're going to have some form of an exponential equation there. Now let's take a look. If we're working with the table of values, how can we identify whether an equation is linear, quadratic, or exponential? So first of all, let's build our table of values. If we look here at this example, we have my given x's are all listed, -3 through +3, and my y's I need to calculate. I can see right from my equation y equals 2x, and if I pick one section here, I can see that that looks like this equation up here, so it will be linear, but let's see how that turns out when we work with the table of values itself. So if I substitute in x equals -3 into my equation, which is 2x, so y equals 2 times -3, then I find y equals -6. I'm not going to write this entire part every time, but I'll substitute in each time. So if I substitute in x equals -2, then y equals -4. If I substitute in x equals -1, y will equal -2. And I'll keep going here, 0, 2, 4, and 6. Now if I'm calculating my first differences here, we have done this in the past briefly. If I'm calculating my first differences, I won't calculate my first one, so I'll just draw a line across there, but I will calculate my second. And what I'm going to work with is my second x value minus my first. So -4 minus -6. We need to be careful there of the double negative, minus a negative. If I put that into my calculator, -4 minus -6, I find it equals 2. And then I'm performing the same kind of calculation for the next ones, -2 minus -4. Equals 2 again. And if I perform the calculation again here, I find it equals 2. I find 2 minus 0 equals 2, 4 minus 2 equals 2, and 6 minus 4 equals 2. Perfect. So if all of my first differences are equal, then I have a linear function. And once I've identified it as a linear function, I don't need to check if it's quadratic or if it's exponential, because it can only be one of these at a time. Next, I have an equation y equals x squared. Again, I can tell right from my equation, this looks very similar to our quadratics, and I notice that my exponent is in fact a 2. So it will be quadratic, and we'll see exactly how that ends up looking. So again, I'm going to substitute in -3 in the place of my x here. So y equals not x squared, but -3 squared, which equals, if I put that into my calculator, a 9. It's a positive 9. We need to be careful that we're including this, this negative within the brackets when I'm substituting into my equation there. And if I substitute in x equals -2, then I'll find y equals +4. And I can keep going like so. Perfect. Now I'll calculate my first differences. Again, when I'm calculating my first differences, I don't calculate the first one. I just work with the next ones here. So 4 minus 9, that's -5. 1 minus 4, -3. 0 minus 1, -1. 1 minus 0, +1. And I just keep going like so. Now I do notice a pattern, and I'll double check that pattern with my second differences here. So my second differences, I'll do the same thing. I won't calculate the first one or the second one this time. And then instead of using my y values here for my differences, I'm going to use my first differences themselves. So my second difference here is -3 minus -5. Again, a double negative. If I put that into my calculator, I find that it equals 2. -1 minus -3 equals 2. 1 minus -1 is 2. 3 minus 1, 2. 5 minus 3 is 2. So I do notice, sorry that they're moving all around here, I do notice that my second differences are equal. That's what a quadratic will look like. Just get some consistency with how I worded it before, are all equal. And finally, let's take a look next at an exponential function. I can see right away from my equation my x is in my exponent. Like I saw up above, that means that I'm dealing with an exponential. So again, I will substitute -3 in for my x, so y equals 2 to the power of -3. And if I'm using a calculator there, it's always a great idea to use your calculator when you're working like this. And I'll end up with, actually, you know what, I'll leave it as a fraction because we've handled things like this in this class, so 1/8. And then if I substitute in -2 for x, I find that y equals 1/4. -1, it's 1/2. 0, anything to the power of 0 is 1. Anything to the power of 1 is itself. And I can see here a pattern. Perfect. So now I'm going to calculate my first differences. Again, I don't calculate the first one. And if I subtract my fractions here, I end up with a difference of +1/8. If I subtract my differences here, I end up with a fraction of +1/4. And I'm just going to keep going like so. Again, I notice a pattern, but I still don't see that my first differences are the same, so they're not the same. Whenever my first differences are not the same, I move on to my second differences. I don't calculate the first two, and I calculate the next ones right here. So 1/4 minus 1/8 is 1/8. 1/2 minus 1/4 is 1/4. Now, the pattern won't always seem so obvious as it seems right here. That's because this is a relatively simple, this is a relatively simple exponential function. But I notice again, my second differences are not the same. That means I move on to my ratio. Okay, so this time for my ratio, I'm going to do something a little bit different. Now what I'm going to do is I'm going to work with my, y values here. And instead of dividing, instead of subtracting like I did with my differences, I'm going to divide. So I won't do my first one, but then I'll do 1/4, which is my second y value here, divided by, brackets around that, divided by 1/8. If I put that into my calculator, I find it equals 2. Now I'll try the next one. 1/2, again in brackets, divided by 1/4. equals 2. And then I'm doing 1 divided by 1 over 2 equals 2. 2 divided by 1 equals 2. And I can see here that I have a pattern. This function, like I said, it is an exponential. I can tell right from my equation here. And the rule that we have just learned is that our ratios, and we've covered this before, ratios are common, which means all equal. Therefore, it is an exponential. Now, the equations, we touched on it up above. All of our linear equations will have an x with no exponent. I can see that in all the examples I gave up here. Actually, except for the one example here, there isn't even an x. If there is no x whatsoever, then it's also linear. All quadratic equations will have an x. Will have an x in the base of an exponent 2. Now let's briefly review, what does that mean, the base of an exponent? Well, remember a power is made up of two parts. So if I have a to the power of b here, then a is my base and b is my exponent. So every single quadratic equation you'll see will have an exponent of 2, an exponent equal to 2, and somewhere within the base, somewhere within here, you're going to see the letter x, the variable x. And let's keep moving. All exponential functions will have an x in the exponent itself. So how is that different from quadratic? Well, this time the x is in the exponent. Before, 2 was in the exponent and x was in the base. So let's take a look. We'll use these 3 rules to identify all 6 different kinds of equations here. I can see right away, okay, let's see. Let's work with y equals 10 times 1 over 3 to the exponent x. Well, does this have an x with no exponent? No, it does not. I see my exponent right here. My exponent tells me that this is not a linear function. All quadratics must have an x in the base of exponent 2. Is the exponent 2? No, therefore it cannot be a quadratic. All exponential functions must have an x in the exponent. Do I have that? Yes, I do. I have an x right there in my exponent, so it's exponential. Moving on. Here, I have an exponent equal to 2, so often that tells me it might be quadratic, and I just need to make sure that my x is in the base. Is my x within the base? Well, the base is everything in the brackets here. I see the x, so it is a quadratic. This one here, just like the first one, I have an x in my exponent. That means it's exponential. No exponents whatsoever this time for d. If there are no exponents whatsoever, then I know I'm working linearly. No exponents again here, so it's going to be linear. And with part f, I can see that I have an exponent equal to 2, and there is an x in the base of my power there, so I know that I have a quadratic. Now, I would like you to continue on here. You have a few table of values. I'd like you to use your differences, use your ratios to find out whether these table of values represent a linear function, a quadratic function, an exponential, or none of the above. So when you're setting these up, the first thing you want to do is write in your first differences. You don't calculate the first one, and then you calculate them right here. If your first differences are not equal, then we move on. We calculate our second differences. Again, we don't count the first two this time, and we calculate our second differences. Always the lower one minus the higher one. That is, sorry, within the chart, the lower in the chart. So that's the second difference minus the first. And if our second differences are not equal, that's when we pull out our ratios and we calculate them. We see if they're common. If they are common, then we have an exponential function. So please solve all four of these table of values. Let me know what kind of function they are, and identify, for these 6 examples down here, identify what kind of function we're dealing with. Thank you.